Hello guys, this is Edward from EdSTEM. Today we are going to be looking at bonding and structures. First, we're going to start with bonding. We are going to look at the different types of bonding. We have the ionic bonding, we have the covalent bonding, we have the dative bonding, or it could be called coordinate bonding, and also we have simple covalent bonding. So we're going to start with ionic bonding. Before we continue, if you find what I'm doing useful, you can support my channel by subscribing to my channel, like the videos. If you have any question, drop your question in the comment section, and don't forget to turn on your notification bell so you get notified whenever a new video like this is dropped. So let's continue. Now, before we dive into ionic bonding, we need to understand the concept behind bonding in general. Why do you think most of these elements want to undergo bonding? I mean, most of these elements they prefer to be on their own, right? They prefer to be on their own, but yet they undergo bonding. And one of the reasons is because they strive for stability. They strive for stability. So most of the atoms are not stable due to the due to incomplete number of electrons in their outer shell. Okay, so because of that, they will some of them will undergo different type of bonding, ionic bonding, covalent bonding, adhesive bonding, and the rest of them. Okay, so now in ionic bonding simply involve the transfer of electron. Okay, transfer of electron from a metal or from metals to non-metals. Okay, so basically metals they have um, few electrons in the atomic shell. Let's say for example sodium, group 1 element or group 1 element, they have 1 electrons in the atomic shell. Let's say for example sodium. Now sodium has configuration of 281. Okay, it has 1 electron in this atomic shell, and this 1 electrons makes it unstable. So it needs stability, and for this for each atom to be stable, it's either it complete this shell to become 8, or it give up this electron. So in this case, sodium will give off one of the electrons to become stable, and it will give it to an electron and to an atom that is readily available to receive electron. Okay, and that lead us to non-metals. Now non-metal, for example, chlorine. Chlorine has configuration of 287. Now chlorine has 7 electrons on the on its atomic shell. Now for it to be complete or for it to be stable, it's either it give up the 7 electrons or it receive 1 electron. And what do you think to be easier for chlorine to do? It will be easier for chlorine to receive 1 electron. So chlorine will receive 1 electron. So in this case then, sodium will combine with chlorine, will transfer electron to chlorine to become stable. Chlorine will receive the electron to become stable as well. Now when sodium transfer the electrons, it becomes positively charged. So when this electron has been transferred, it becomes positively charged, that is sodium ion. And when chlorine has received 1 electron, the 7 the atomic shell then becomes 8. So by doing that, it becomes negatively charged. So this kind of bonding is known as ionic bonding. So we're going to look at how to represent ionic bonding because it's very, very important, especially in your um, examination. So we have sodium atom, okay, with configuration, okay, 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now this is 10, so it remains one more electron. Then we have one electron on the outermost shell. So we're going to use dot and cross, okay, to represent um, the ionic bonding. So that's what you're expected to do. Okay, so this is our sodium atom. This sodium atom plus our chlorine. So we're going to use a cross for chlorine. Chlorine is 287. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have 7 electrons on the outermost shell. 1, 2, 3, 4, 5, 6, 7. So this is chlorine. Yeah. So when they combine, we will have sodium chloride. Okay, so we have sodium, one, two, three, 4, 5, 6, 7, 8, 9, 10. Now it has given off one electron, right? So it becomes positively charged. Okay, then the chlorine, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have 11, 12, 13, 14, 15, 16, 17. Then plus the one electron received from sodium, we have it here, and that makes it 18. That makes it to become complete. Okay, so we have our chlorine ion comes negatively charged. Okay, so that is ionic bonding. So here we have sodium chloride. Okay, now there are a couple of things you need to note in this ionic bonding. When sodium gives up electrons to become positively charged, and then chlorine receive the electrons to become negatively charged, these two are oppositely charged, and we know that oppositely charged attract each other. So because of that, there will be a force of attraction between these two, all right, and that leads to um, ionic bonding. So that couple of things we need to note here. The charge of the ion actually is related to the strength of the ionic bonding, right? So which means that the greater the charge of an ion, the greater the force of attraction. And if you have force of a great force of attraction, it means you are going to have a stronger ionic bonding. You're going to have a stronger ionic bonding. So you need to have that in mind. Also, there's another factor as well that affects the force of attraction, and that is the ionic size of the charge. The size of the charge. So if the charge has, if the size of the charge is greater, okay, that will lead to a weaker force of attraction. And the reason is because of the distance between that, basically because of the ionic distance. So ionic radius, okay. The reason is because of the ionic radius. But if the size of the charge is smaller, okay, it will lead to a greater force of attraction, which in turn will lead to stronger ionic bonding. So you need to take note of these factors. Now let's look at covalent bonding. This kind of bonding involve the sharing of electrons between two non-metals. Okay, between two non-metals or between non-metals. Okay, so now we know that non-metals cannot give off electron. Okay, and they can only receive electron. Mostly they receive electron, but then in the case whereby they don't receive electron, I remember that they need to be stable. They can also involve in electron sharing for them to be stable as well. All right. Now they can share multiple electrons to form multiple covalent bond. Okay, these are the things you need to take note of. Okay, they can share multiple electrons to form multiple covalent bond, and the force of attraction between, there is a strong force of attraction between the shared electrons and the nucleus. Okay, so in covalent bonding, there is usually a strong electrostatic force of attraction between the shared electrons and the nucleus. Okay, so now if you have two electrons shared, okay, now this will form a single bond. Okay, and if you have four electrons, okay, two from each side of the non-metal, it forms double bond. And if you have six electrons, okay, it forms triple bonds. So this is how covalent bonds are formed. Now we're going to look at how to represent covalent bonding with examples. We're also going to use dots and cross to represent this bonding as well. So example of covalent bonding can be found or can be seen in chlorine molecule Cl2, and this is formed when two chlorine atoms shared electrons. Okay, so now we have chlorine to be chlorine has a configuration of 287, right? So we're going to draw the configuration of this um, atom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it remains 7 electrons. Then we have 7 electrons. 1, 2, 3, 4, 5, 6, 7. Then the second chlorine atom as well has configuration of 2, 8, 7. Now let's represent the configuration as well. We're going to use star or cross. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then 7 electrons. 1, 2, 3, 4, 5, 6, 7. Okay, now when they combine, they share electron. Okay, and we're going to have this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then 1, 2, 3, 4, 5, 6, and 7. Okay, then it combines with the shared electron with this second um, chlorine atom, and the second chlorine atom we have the outermost electron. Let's start with the outermost electron. 1, 2, 3, 4. It has 7, right? 5, 6, then 7, right? It shares the electron from the outermost shell. Then we have the 8 electrons on this second shell. 2, 3, 4, 5, 6, 7, 8. Then the 2 electrons. 1, 2. So 2 electrons are shared, one from each of the atom, right? So this will lead to single bond. I hope that makes sense. Let's look at another example. So let's look at oxygen molecule as another example. Just like we have in chlorine, 2 atoms of oxygen combine together to form oxygen molecule, right? And we know that the configuration of oxygen is oxygen has atomic number of 8, right? So the configuration will be 2, 6, right? Now let us draw the dots and cross diagram for the oxygen molecule. So the first oxygen is going to have, we have that the first one is have two, this is the nucleus, then 2 electrons, 1, 2, and then 6 electrons, right? So 1, 2, 3, 4, and 5, 6. Okay, plus the second one, we're going to use cross to represent that. This is the nucleus. 1, 2, 3, 4, 5, 6, and 7, 8. So when they combine together, these 2 and these 2 will be shared. Okay, so total they will share 4 electrons in total. So we're going to have this structure. We're going to have this diagram. So we have, for this, we have 1, 2, 3, 4, then 5, 6. Okay, then we have the second oxygen, and that will be 1, 2, 3, 4, 5, 6. Okay, so if you're going to draw the nucleus, the inside, we have that 1, 2, and also for this one we have 1, 2. So as you can see here, the share total of 4 electrons, the share total of 4 electrons, 2 from each side. So in this case, now oxygen molecule will give or produce double bond, double covalent bond, double covalent bond. Okay, so that's another example for covalent bonding. So in covalent bonding, there is a relationship between bond length and the force of attraction. Okay, and the force of attraction. And it is that the shorter the bond length, okay, the greater the force of attraction. And the reason is that when the bond length is shorter, that the atoms appears to be held closer together, so that results to a greater force of attraction. Okay, so the shorter the bond length, the greater, okay, force of attraction. Okay, so and the longer the bond length, the um, the lesser the force of attraction. Okay, now how do we know bond lengths that are shorter or are longer? Now, single bond appears to have the shortest bond length. Okay, so single bond have short bond length. Okay, white double bonds and triple bonds have longer bond length. Okay, so it means that in single bonds you're going to have the greatest force of attraction in single bond because it has the shortest bond length, followed by double bond, double bond, and lastly by triple bond. Okay, all right. So that is what's taken note of as well. So let's look at bond, dative or coordinate bond. So now, in this kind of bond is formed when both of the electrons in the shared pair are supplied from a single atom, right? So it is usually indicated using an arrow, okay? And it can be found. Example of this kind of bond can be found in ammonia. Ammonia actually has an unpaired electron, sorry, a lone pair of electron, and this lone pair of electron can form a dative bond. That's a lone pair of electrons. Okay, these lone pairs of electrons can form a dative bond when it reacts with hydrogen ion. Okay, when combined with hydrogen ion, it can form um, ammonium. It forms ammonium ion. Okay, so we have this to represent that. So this is okay, and this shows that this is ammonium ion, and the arrow indicate the dative bond or coordinate bond. Okay, now once a dative bond is formed, they have the same properties as covalent bond. Okay, the same properties regardless of their bond length or bond strength. Okay, they both they're gonna have the same properties as covalent bonds. Now, while presenting the structure of dative bond, it is important to note that you don't use dots and crosses. Okay, you don't use dots and crosses. It's either use dots or crosses. And the reason is because the shared electrons are coming from a single atom. So because of that, you don't use dots and crosses. You use either this or this. So let's look at the example. Let's look at the structure of ammonium ion. Okay. Now ammonium ion is as a result of the lone pair of electrons rather from ammonia. Okay, reacting with hydrogen ion. Okay, and that gives us ammonium ion. Right. So let's look at that. Now nitrogen and the first shell contains 2 electrons, and the second shell contains 5 electrons. So we have 1, 2, 3, 4, and 5. Right now, this nitrogen combines with three shared electron with 3 hydrogens to form ammonia. So we are going to use another color to represent hydrogen. Let's use white. So here we're going to have hydrogen. So, and this is the electron from hydrogen. As you can see, I'm still using dots, and also here hydrogen, and here hydrogen. So this is the electron. So these two lone pair of electron is what reacts with hydrogen to form ammonium ion. So when that happens, we're going to have this. So we're going to have this, or this will be for hydrogen. So this is ammonium ion. I hope that makes sense. So lastly, let's look at simple covalent bond. Okay, so basically this is the bond that is holding simple molecules together. Okay, let's say for example we have um, H2O. All right, now the H2O itself, the bond in H2O is covalent bond. The bond is strong, it's covalent, right? Okay, but when we have so many molecules of H2O, right, the bond that is holding the so many molecules of H2O together is known as simple covalent bond, and is a weak kind of force, or is a weak. It's a weak. It's a kind of intermolecular force. Okay, so it's an intermolecular force that is holding the simple molecules together. So, for example, we have H2O, and let's draw the structure. Let's try and represent the structure. We have this water, and if we have another water molecule, okay, you have another water molecule. Okay, now the force, the intermolecular force that is holding the two molecules together, the simple molecules together, is known as simple covalent bonds, and it's a van der Waals force. Van der Waals force. It's a very weak force, and the bond can be easily broken. Okay, so that is what simple covalent bond is all about. Example can be found also in CO2 as well. CO2, all right? We're going to look at the properties of compound formed from this bond, and we're going to start with, let's start with the last one, which is simple covalent bond. So, like we said, this bond, the bond is an is a weak intermolecular forces, right? It's like a weak intermolecular force. So basically, the compounds, this kind of bond has low melting and boiling point, low melting and boiling point. Okay, and that's because it requires little energy to break that intermolecular force. All right, and also they do not conduct electricity. They are poor conductor of heat and electricity. Okay, and the reason is because they don't have there is no free moving electrons. Okay, there is no free moving electrons. So let's look at dative or coordinate bond. The properties. Now remember that we said that dative bond will have the same properties as as covalent bond, right? So basically, this is going to have the same property as covalent bond. So what are the properties of covalent bond? Okay, now covalent bond has strong um, force of attraction, right? So it's going to have high melting, and boiling point. Okay, and they are also poor conductor of heat and electricity because they don't have free moving electrons as well. So they are poor conductor of heat and electricity. And also they are insoluble. So the compounds formed from this bond they are insoluble in water, but soluble in polar organic solvents. Okay, so let's look at the properties of ionic bonding. So ionic bond, now they have high melting and boiling point. Okay, high melting and boiling point. All right, and they are soluble in water. They are soluble in water. And they are good conductor of heat and electricity. Of heat and electricity. And also the compounds, they are hard and brittle. Hard and brittle. Okay, and they have a crystalline structure. Crystalline structure.